2, we're looking at how earthquakes are measured. You should be able to identify the characteristics of seismic waves. You describe how earthquakes and a seismograph works. Identify the strength of an earthquake using different scales of earthquakes. Okay, so seismic waves. We've talked about these. Faults occur between the surface and 70 kilometers deep. The focus is the point of origin for an earthquake beneath the surface where the rocks break and move. So the focus is underground. The focus is where the actual shifting is occurring that's causing the earthquake to occur. The epicenter is above the focus at the surface where the earthquake actually occurred. So directly above our focus would be our epicenter. We're going to be identifying where epicenters are later in the lesson, and doing some triangulation to do so. But I'll explain that when we get there. Most violent shaking occurs at the epicenter. So obviously we're not underground. We're not going to feel the stuff underground. It's the waves that are hitting directly above our focus. That's where the strongest hit is going to be. Seismic waves are earthquake waves, and it gives lots of information about the interior of the earth, which we learned 2 units ago. Primary waves are P waves. Primary waves are the first waves that arrive, and they travel the fastest. They can travel through solids, liquids, and gases. Again, this is review. They can be recorded from locations throughout Earth. They move through the Earth at different speeds based on density. They are faster when it's more dense and slower when it's less dense as far as the material that they're going through. So here's a P wave, and P waves just go back and forth in the same direction. So you can see how this is going this way, this is going that way. These are further apart, and these are going back and forth as well. So when you think of this movement, I want you to think of a slinky just going back and forth on a level table where it's oscillating. The rock particles are going to push forward and other particles push back, causing compression, and they're going to bounce back and forth again. So that is our P waves. Our S waves, or secondary waves, do not travel through the earth as fast as P waves. They travel through solids. They don't travel through liquids. They speed up through denser materials. The S waves cannot be recorded everywhere due to the liquid layer. So there is that shadow that we talked about when we talked about the layers of the earth. They move side to side and cause the most damage. So for this one, it's going to go up and down as it's moving, or back and forth, however you want to say it. Either way, it's moving in 2 directions. So it's going to be moving forward, but it's also going to be going back and forth while it's moving. So kind of like vibrational, I guess you could say. So think about that slinky. If you have one side here, and you and a partner are like waving it back and forth, kind of like a jump rope otherwise, like where you're just playing with the jump rope, swinging it back and forth, making it make waves in that manner. There is another wave called the L wave that we are aware of, but this one doesn't get used to help determine location of earthquakes or measure the strength quite so much. But there is an L wave that exists. But for the purposes of this class, we won't be going into the depth of the L wave. The L wave has a circular type motion, so it's kind of a rolling motion. Seismograph is an instrument that detects and measures seismic waves. It consists of a weight attached to a spring or wire. There's a pen attached to the weight, and any movement is then going to record on the piece of paper below it. So here's the pen. This is going to rotate. It's going to have new paper, and any movement of this weight is going to be recorded based on the vibrations. So we'd have a wavy line to determine what's happening with the movement of the earth. Now this image is kind of cool because it shows, you can see where the fault line is based upon the stuff that's planted here. So you can tell that there is either a shift of this part to the right, or this bottom part got shifted to the left, or a combination of both, because you can see that it kind of jogs right here going all down this line. Okay, so we can see some evidence of faults. A seismologist is a scientist who studies earthquakes. They can determine the strength of an earthquake by studying the heights of the wavy lines in the seismogram. So here's our seismogram or seismograph. The P waves are always smaller just because of the fact that they're only moving back and forth. They're not moving that up and down like the S waves. So the S waves, because they're more damaging, you'll notice that they cause more movement when the seismograph is being made. The height on the lines is used to calculate the strength of the earthquake. We will be doing that later. The higher the waves, the stronger it is. The lower the waves, the weaker it is. And previously estimated strength is based on observations of destruction. So we have two different earthquake scales. There's the Richter scale, which is a calculation based on the waves. And it was created by Charles Richter and Bino Gutenberg. And it goes by a logarithmic scale. For each increase in a number, an earthquake is 10 times stronger. So for every number you go up, so if we're going from 2 to 3, 3 to 4, 4 to 5, so on and so forth, it's going to increase 10 times stronger going from the level 2 to the level 3. 10 times stronger by the time you go from level 3 to level 4. So you're talking a whole lot stronger when we get up into the 8s. So it would be 10 times for every single number going higher. Estimated number each year. Again, we talked about how the lower destruction, the not as damaging earthquakes, the weak ones, are more numerous. And then our strong ones, we might only have one every 5 to 10 years. So many, many fewer.
To infinity and beyond!
So that's just to stress that there's no upper limit. This can keep going and going as far as our magnitude goes. The Mercalli scale is based on witness observations. So you'll see that we've got our intensity of 1 through 12 down here. And our equivalent magnitude, so the Richter magnitude is here. So 1 to 2, 2 to 3, so on and so forth. These are a little bit different. Not terribly off, but obviously our Mercalli is going to have a more sensitive change, whereas our Richter is more severe. Witness observations, you can read through some of these, like the low levels, you're not really feeling them. Upper floors on buildings might feel them, but it's not anything that they would really even get overly concerned about. When you get into level 5 to 6 or 6 for the Mercalli, it's felt by everyone, can be difficult to stand, furniture might be moved. Level 9 for Mercalli and 7 for Richter, we get considerable damage. And when we get into the 11 for the Mercalli and the 8 for the Richter, we're talking total damage. So this is on your notes, and you can read through these. You'll be using these when we do one of our activities later. Earthquake strength. Oh, and to mention, the strength of the earthquakes that were in the middle of the United States, they were like 7 or 7 to 8. So here we go. We've got wholesale destruction. We've got considerable damage, landslides, ground's badly cracked. So that's some pretty good damage in there. Okay. The damage of an earthquake depends on the earthquake strength, the kind of rock and soil under the area, the population of the area, because obviously if there's more people, more buildings, there's going to be more damage. If it's an earthquake out in the middle of nowhere, you're not going to have near the damage. And typically our damage is measured in like having to replace whatever goes wrong, which is going to be more people related stuff. Whereas if it were out in the middle of a forest somewhere and it's a natural habitat, yeah, it might cost money to replant the trees, but it's not like in the middle of a city where humans are like, oh, we need to replace all these buildings and it's going to cost this much. So we look at it more from the human standpoint. Time at which the earthquake occurs can also have an impact on it, as to whether people are prepared for it or not. whether they can respond to it or not. That could impact whether there's fatalities and such. Okay, so here we've got an image that would show what kind of damage we could potentially expect for earthquake strength. The main reason this area is highlighted is because of those New Madrid fault zone. So like any of these areas that have strengths, it's because of either current or past earthquakes that could have happened or other things that could have been going on. Now, if we were to look at this today and take into consideration fracking, we'd have a whole lot more down in the Texas and Oklahoma area, guaranteed.